sad lecture that is. Yeah, I'm saying goodbye. I have to tell you, I will not make it to the question and answer session this afternoon because I didn't realize and I booked my flight very close. So if you have questions after the lecture, you can just attack me before or during lunch or during coffee or whatever, or after the lecture, because I will not be here. Of course, you can always write to me, as Gabriele did. I will answer to you. So, but before that, let's produce some questions, right? So my last lecture is on dark matter and WIMPs. WIMPs are the standard and most beloved dark matter candidate that has come out of our brains for a number of good reasons that I want to convey to you. So, so at least one can list these three big motivations, I think, for how much we all love WIMPs. First of all, from the theoretical point of view, we are very much concerned or biased by the hierarchy problem. The fact that we are pretty sure, we have a very strong feeling that the standard model of particle physics is not the final model of particle physics. We expect new particles, new fields beyond the standard model. And from all we know about quantum field theory, some of these particles may just contribute to the Higgs mass through radiative corrections. And these radiative corrections give typically a Higgs mass, a mass which is of the order of the new high energy physics scale that you consider. So, and this is, for instance, I don't know, so if you are very brave, you can even think that even gravity, even quantum gravity might even produce quantum corrections to the Higgs mass that would be of the order of the Planck mass, 10 to the 19 orders, 10 to the 19 GeV, so 10 to the 17 GeV orders of magnitude above what we have, what the Higgs mass is in reality, or the electroweak scale is in reality, right? So this is so-called hierarchy problem. In principle, I mean, we can live with theories like this. We can just, of course, renormalize these divergences to be zero. To cancel the high. We can renormalize these divergences or these contributions with the Higgs mass in principle, but this means that we have to put a Higgs mass in the three-level Lagrangian, which is huge compared with these radiative corrections. This is extremely unlikely. We don't like at all, and actually we would like to have some kind of theory that explains why these radiative corrections to the Higgs mass coming from high energy scales, they are not big. They are under control. And we want this, of course, and we want this high energy physics, perhaps the one canceling these contributions as close as possible to the electroweak scale. So to explain that the Higgs mass is actually happening at the electroweak scale. So then we have a second motivation now from the phenomenological point of view that I will tell you a little bit about, which is the so-called WIMP miracle. That when we put new physics, so a new particle that is stable, a dark matter candidate, and we compute the thermal freeze-out in the early universe, so we compute the relic abundance of these particles, as we will see, and we have partially seen, so the relic abundance of these particles tends to be of the order of the observed relic abundance of dark matter, so this 0.3 of the critical density, if the particle, if the new dark matter particle has a cross-section which is of the order of electroweak cross-sections, okay? So if this new particle that we invent has a cross-section of the same order than the electroweak cross-sections, we might reproduce very nicely, very easily, the relic abundance of dark matter that we observe in the universe. And then the third reason, which is this is quite anthropocentric, is that with these WIMPs, we have a wealth of complementary approaches to study their physics. We can use essentially indirect detection. I will tell you a little bit about, in which relic dark matter particles that are floating in our universe can still annihilate to convert into standard model particles, and we can see these effects. Or they can scatter with dark matter with standard model particles, if we put them in our detectors, or we can just produce them in colliders And these three techniques, they can give us information if this new particle has something to do with electroweak scale, has electroweak scale masses and electroweak scale cross-sections. It's much more difficult to get this wealth of complementary approaches if this particle has a mass of the 10 to the 15 GeV, it has much smaller cross-sections. So with the spirit of Occam's razor, of course, we like to explore dark matter candidates as well, that actually we can just, that we can get some large number of signatures, potential ways of studying them, okay? So these are the three, in my opinion, three big appeals of weakly interacting massive particles. And now you know what they mean, more or less. Particles related with electroweak physics, or physics at the electroweak scale, that might have electroweak cross-sections for annihilation. Of course, they have to be stable to be dark matter. And yeah, so let me just go a little bit to the early universe and study the production of these particles, although this is something that, we have already heard a bit about, but I think it's never bad to repeat, so that we can understand also the so-called WIMP miracle. So the idea is the following. The idea is, in building many of our theories beyond the standard model, we might encounter these good dark matter candidates, okay? And these good dark matter candidates have to satisfy from the particle physics point of view a few requirements. First of all, they have to be more or less stable, okay? And they have to have, they have to be stable, and I have a blank now. I forgot what I was going to say. Okay, well, let's start again. So we are they have to be stable. Yeah. So okay. So if these particles are stable, but still they have to be produced in the early universe somehow. And they are related with electroweak, so they have relations with electroweak physics through electroweak physics to the standard model. If we go back sufficiently enough in the early universe, we will reach a temperature, or we might think that the universe had a temperature enough to produce these particles, okay? So these particles are stable, so they might not decay or produce in one, so we are going to consider that they can annihilate between themselves. I'm not going to make a distinction between particles that have an antiparticle or particles or Majorana particles that they can be their own antiparticle. So for me, it's going to be more or less the same here. But the idea is, yeah, since they are related with electroweak scale physics, if the temperature of the universe was very high at some point, standard model particles will be able to produce these new particles, and of course, the inverse process will happen. And if this process is fast enough in the very early universe, you will get a thermal abundance of my WIMP, right? Now the idea is, so this is very interesting and very completely different to the axion-like particle case that I told you before. So these interactions are sufficiently strong as to produce from standard model particles a relic, so an abundance of these particles of the order of the thermal abundance of other particles. So these particles will be completely in thermal equilibrium with the standard model particles. And what is going to happen to them is that as the universe expands, these interactions, in principle, if they are strong, they will keep the thermal abundance between standard model particles and them. But at some point, when the temperature becomes of the order of the mass, right, of this WIMP, the thermal equilibrium abundance is, of course, suppressed with respect to the abundance of massless particles. This is a pure thermodynamics, I guess. So the maximum entropy state, if you have a bath of massless particles and very massive particles, the maximum entropy state is to have a lot of their energy in massless particles, right? That they can have a much larger phase space. If you put a lot of energy in one of the heavy particles, this is a very ordered state, right? So as the mass as the temperature becomes much more than the mass, the thermal equilibrium tells you that the abundance of these massive particles has to be suppressed. And it turns out that it's exponentially suppressed. And this is what you see in this plot, where I show this is the number density of WIMPs in equilibrium divided by the entropy density. Okay? And the entropy density, you know that this is essentially just the number of photons multiplied by the number of, the density of relativistic particles, essentially. And this is an invariant if the universe, the co-moving abundance of this of entropy is an invariant over in the expansion of the universe, as Javier told us. If the expansion of the universe is sufficiently slow, it's always adiabatic, it's kept in thermal equilibrium, right? So what you see here is that, yeah, very low mass divided by the temperature. Of course, this particle is relativistic, and you want to have a lot of them. A thermal abundance is generated at some point, but then at some point, the thermal abundance of these particles is very strongly suppressed, and when this happens, this process has to be efficient enough as to maintain the equilibrium configuration, right? Which is not having many of these WIMP particles. But of course, these reactions happen only at a rate, and for this reaction to happen, our WIMP has to find a partner to annihilate, right? And now you can think that in a universe in which the universe is expanding, so the density is decreasing, but also one has to keep up with an exponentially decreasing number density. At some point, this reaction, as strong as you can make it, it will fail to annihilate all the WIMPs, and at some point, you will get some relic abundance of these WIMPs, right? So the dynamics of this system is just very nicely represented by a Boltzmann equation. You can understand, yeah, this is the rate of change of the number density of WIMPs. This factor here just tells you that if nothing happens, the number density has to decrease because the universe is expanding, right? So the density has to decrease. So if this would be 0, this would give you a solution, which is that the energy density decreases as R, so initial density divided by R cubed. So this is just the dilution due to the expansion of the universe. And this essentially represents annihilation. This is proportional to the density. See, this n is the density of these particles. So this gives you some decrease in the number density. And the production is due to standard model particles that will try to keep this density at the equilibrium value, right? And you can see that this is, so having n equals n equilibrium, the density of equilibrium is an attractor of this equation, right? So actually this is the attractor as a function of temperature. But however, at some point, this cross-section is, so this number density, the number density of, this number density is so small that this term here becomes essentially 0, and then the number density freezes out. Okay, that's very well known. Let me just put you an example that I think has been floating around a bit during these lectures, which is, let's consider that this new WIMP has a very simple, so it's a very simple type of new particle, a fourth neutrino, or a neutrino that couples to set bosons, okay? A neutrino that couples to set bosons is definitely a weakly interacting electroweak interactingly particle, and we can work out very nicely the example again. So I'm going to consider essentially my new neutrino and giving electrons or giving other neutrinos, giving other fermions through a set exchange at relatively low energies. This cross-section is, of course, has to be inversely proportional, has to be suppressed by the propagator of the C, right, square, at the amplitude level, but the probability is amplitude squared. So you have a suppression of the mass, the inverse mass to the 4, and you have 4 vertices, so you have some coupling to the 4th. In order to make this into a cross-section, we have to So we will find, of course, extra powers of the energies involved in this annihilation. And we can, for the fun of it, we can consider two regimes. One relativistic regime in which my neutrinos and the final state particles are just relativistic. So the important energy scale is their own energy, which will be, as Javier was saying, it will be of the order of the temperature, right? But in the limit in which these particles are relatively non-relativistic, these also these powers of the energy I have to put in order to have a proper cross-section is going to be the mass, the mass of the neutrino, of my heavy neutrino, right? Very good. So now we can essentially calculate the relic abundance through a very simple trick. So the idea is that at the freeze out, so the freeze out of this dynamics corresponds to essentially the case when so we are more or less in equilibrium. We are about to exit the equilibrium with the density of WIMPs. So we have the density of equilibrium, but then the probability of one WIMP to find his partner is of the order of the time of the universe, okay? And if we wait a little bit, so if we wait a little bit, the next WIMPs to annihilate already, they will have a probability which is much smaller than 1 to find his partner, okay? So this is more or less the condition. The interaction rate divided by Hubble equals 1. Remember the Kefir's lectures, at which some reaction freezes out in the early universe. Okay, so this equilibrium density, so the idea is that the freeze-out density of my WIMPs is going to be like the equilibrium density when the interactions stopped being effective, okay? So that's like saying that this freeze-out density is going to be like a very close by equilibrium density. Very good, and we can compute the relic density today, which will be, so the mass density of dark matter will be the mass of one dark matter particle times the number density today on average. But this we can write with the definition of this yield that I gave you before. Instead of using the density, we can use the yield with density divided by entropy, and is conserved if the universe expands adiabatically. Okay, and this is a dimensionless number, which is a useful quantity. It's a dimensionless number, and if the universe expands adiabatically, it doesn't change. Tells you the number of dark matter particles per entropy. So here there's a mass missing here. Of course, the density, so the yield today is assumed to be the yield at freeze out, and so we can write this expression with the mass that is missing, as the density in the freeze out divided by how much the entropy has been diluted in the expansion of the universe. Okay, so we can find the two scenarios depending on whether now this relation starts to this relation starts to be of order 1 because the cross section becomes very small, or because the number density becomes very small. Okay, there are these two regimes. So this thing, normally high temperatures is much larger than 1, and then it can be the cross-section or the number density that drives this decoupling. So let's imagine that this is the cross-section that is so weak that even when particles are relativistic and the density is quite abundant, this thing can drop to be of order 1. Then we can have the freeze-out of this interaction when the particle is relativistic, because of cross-section. And then in this case, the equilibrium density at freeze-out is the thermal density, right? So then we can immediately get that the density is just, the density today is using this formula with the mass, of course, is the density at freeze-out divided by entropy at freeze-out multiplied by the entropy density today. But the important thing is that the number density of a relativistic species at freeze-out essentially has the same parametric dependence like the entropy. So it depends with the temperature at freeze-out with the cubic power and the entropy density as well. So these two things cancel, And the only thing that you're going to get is that the density is essentially proportional to the mass, so to the mass that these particles have today, of course. But it's going to be inversely proportional to the number of degrees of freedom that we're contributing to the entropy density. So that's the only interesting parametric dependence that we get in this relativistic limit. The most interesting limit happens when this particle decouples, not because the cross-section is small, but just because the number density is decreasing exponentially, the particle is becoming non-relativistic, and then even with a large cross-section, this interaction rate drops to 1 and smaller. So this happens when the particle is non-relativistic, and here the trick is to use this expression to compute the freeze-out density. We use this expression that the density at freeze-out is more or less Hubble divided by the cross-section. So we use it here, and then we substitute. You know that the Hubble scale in a radiation-dominated universe is going to be proportional to the square root of the energy density. The energy density depends, like the temperature to the 4. So the Hubble scale depends with the temperature square in radiation domination. But the entropy density at freeze-out is essentially depends only on the temperature at cube. So then you get this interesting cancellation or grouping of terms. The density becomes, first of all, inversely proportional to your cross-section, but also is proportional to this factor over here. Sorry, this is mass divided by this is mass divided by temperature. I don't know what I was thinking at 6 in the morning today. So this is the other way around, right? But what happens is that when a particle decouples non-relativistically, the abundance, the freeze-out abundance, is changing exponentially with this ratio, with the mass divided by temperature. So it is so fast that even a very small change in mass divided by temperature, when this is already a factor of order 20 or something like this, a small change in mass over temperature has a drastic effect on the equilibrium density. So then what this means is at the end is that this ratio is very weakly dependent on the cross-section. Okay? This is going to be a number that is relatively large, perhaps, but it's only going to depend logarithmically on the rest of the parameters of the problem, because only a minor change will give you a large effect in this formula. So then what we get is that the density today of these particles is inversely proportional to the cross-section. It does not depend parametrically on other, it has a few other parametric dependencies, but this is the most important, okay? The larger the cross-section, the longer I can keep my particles annihilating in thermal equilibrium, right? The larger the cross-section, I can follow this curve for a longer time, and therefore I will have a smaller relic abundance. So these two regimes, they can be represented in this graph of the amount of dark matter in these neutrinos as a function of their mass, which is called the Lee-Weinberg curve, in which you recognize the relativistic decoupling and non-relativistic decoupling, because in the relativistic decoupling, the relic abundance is proportional to the mass, remember? Essentially, with this calculation, you see that essentially all the particles that decouple relativistically, they have an abundance which is the thermal abundance. So the number of them is typically thermal, right? This is what we obtained here. It's only suppressed by the number of degrees of freedom of the entropy when they decouple, of the entropy density when they decoupled. So this is the only thing that makes the difference. And of course, if you compute the mass density, you have to multiply by the mass. This is why it makes this mass power here. On the other hand, in the regime where the neutrinos decouple relativistically, the relic abundance is inversely proportional to the cross-section, and this is a general result here. I have not used my cross-section above, but it turns out that my cross-section is actually proportional to the mass squared, right? So then what I get is this 1 over mass squared behavior here. And it turns out that now, if we want to have these particles as dark matter, we have, of course, 2 solutions. One solution with something like 10 electron volt masses that you know. This one would be precisely this would be exactly the type of neutrino dark matter that people was thinking about when they first discovered dark matter. They thought, oh, neutrinos can be just the dark matter. This was the mass, the range of masses that would allow neutrinos to be the full amount of dark matter. However, you know very well that this is a problem with this has a problem with structure formation because neutrinos are produced relativistically. We have seen it once again, and they free stream for a long time. But we have this other solution at very large masses, in which these extra neutrinos could be also the dark matter, and they decouple non-relativistically. However, this essentially this has not been seen at LEP. As you see, this corresponds more or less to 10 GeV. So the C boson that was produced at LEP, it could have decayed into this new particle, right? And it didn't show. So essentially this was excluded by LEP. But this has served us to learn a bit about the calculation of the relic abundance of a particle that decouples non-relativistically. Okay, a particle that is in thermal equilibrium, and because of its mass becoming much larger than the temperature at some point, it cannot keep up with the equilibrium density, and its abundance freezes out. And so if we put all the numbers so the numbers that I have not put in the non-relativistic calculation, you get the following formula. You get the relic abundance today of cold dark matter. By the way, of cold dark matter. Now you know. I explained to you the other day what is the calculation of the free streaming length and free streaming velocity of a thermally produced particle. Remember, and we started to have problems with. Also, we started to have large free streaming lengths for particles of mass of 1 kilo-electron volt. But now these particles, they have 7 orders of magnitude more than the particles that were starting to have some problem. They will not, they will have much smaller velocities. So these particles are really cold dark matter. So if you put the numbers, you get this expression. And actually, if you take a particle, so if you just take a particle, we will call a WIMP, a weakly interactive massive particle, and you just put, you compute the cross section as we had done before, just a coupling constant to the 4th power, electroweak mass scale in the denominator, and the right amount of factors of pi to suppress it, you get precisely up to these imprecisions, the exact value that you need to get the right relic abundance. Okay, this is the so-called WIMP miracle. The apparent coincidence that we really need physics at the electroweak scale to ease our issue with the hierarchy problem, and oh marvel, these particles, if they are stable, and the universe was hot enough to produce them in the early universe, they will actually be produced, and some of them that will be left over, and this relic density of these particles matches the typical abundance that we have seen in the universe. So this is the so-called miracle. Very good. So so let me just very briefly tell you about what theories, what candidates we have for such a WIMP. The first of all is it comes when we speculate about supersymmetric extensions of the standard model, which are perhaps the most attractive physics beyond the standard model that we could have dreamt a few years ago. Maybe now people doesn't like them so much because supersymmetry is not showing at the LHC, but still, I mean, the case is really compelling and lovely. So the idea is that for each particle of the standard model, for sure, we will have a supersymmetric partner with a different spin, okay? So we are doubling the particle content of the universe, or of nature, and this eases very nicely the the hierarchy problem, because the contribution, because the contribution of one of these particles, and now by extension, all the particles in nature will be supersymmetric, will always have a partner. So the contribution of one of these particles to the mass of the Higgs is always cancelled, or at least the divergent part is cancelled by its superpartner. So yeah, if nature is supersymmetric, there are no large corrections to the Higgs mass, as long as these superpartners have masses which are not very different. So that's why we want to have them at the electroweak scale. Bad thing is, of course, supersymmetry would be a good symmetry, and then if it would be a good symmetry, all the superpartners will have the same mass than standard model particles, and this is not the case. We have only observed half, the first half of the supersymmetric world. The second half still remains elusive. So we have to, so these superpartners have to have higher masses, and breaking supersymmetry is a very ugly and dirty business. However, well, this is what it is. Now we have to find among these new particles some reason for one of these particles to be stable, and this came from the hand of so-called R parity. R parity would be a multiplicative parity that standard model particles have plus, and supersymmetric particles have minus one. And in any reaction of a theory in which this R parity is conserved, the product of the R parity of the initial state and the final state particles has to be conserved. So this makes automatically the lightest supersymmetric particle a stable candidate, because a state of one supersymmetric particle has R parity minus one, and yeah, it can only decay to standard model particles, but all the standard model particles have parities plus one. So you cannot go from minus one to plus one. And if you are able to build models with R parity, then our lightest supersymmetric will be a perfect dark matter candidate. So it turns out, of course, we want to some extent that these particles are also neutral, to have less interactions with light that would render large interaction cross-sections with our detectors and so on. So the best candidates are the neutralinos, and well, you can also think about neutrinos. Neutralinos are essentially combinations of all the spin 1/2 superpartners, which are the companions of the gauge bosons and the Higgs. And neutrinos are the superpartners of the neutrino, and these are bosons, okay? Very good. So there are also a couple of very interesting, I think, motivations for supersymmetry, besides the hierarchy problem. Of course, one very strong motivation is that, at least until yesterday, I thought it was the case, but I'll tell you two things. In principle, string theory is a very nice candidate for unifying the standard model of particle physics with quantum gravity, right? And string theory requires supersymmetry to some extent. Now, yesterday I was talking with Saul Ramos, and he told me, no, this is not true. So actually, you can have superstring theory without supersymmetry. You can just put supersymmetry in one brain that you don't need for anything. But with this supersymmetric part of your theory, you cancel all the anomalies, you make the theory consistent, and you will never see supersymmetry, not even at very high scales. So now you know the caveat, but this would be an argument that many people might use for you. And the bad thing is that, of course, well, and the second very nice argument is that actually, if you put all these particles at the electroweak scale, somehow at the electroweak scale, now the running of the couplings of the standard model changes in such a way that actually all the three couplings, the U1, the C2, and SC3 couplings, they meet at some point at a very high energy scale, which is our excuse to consider that these interactions could be just three ways of saying the same thing. So the three interactions could be unified in a much larger gauge group. So these things are extremely appealing. And this said, the bad thing is that supersymmetry breaking is a bitch. You can actually, you can have millions of, you can have plenty of parameters already within the minimal supersymmetric extension of the standard model, which is the one I wrote you here, without introducing new Higgses or new fancies. You actually need one more Higgs, this you know. It has many parameters and many possibilities. It's very difficult to find, to search for supersymmetric dark matter in a generic way because, yeah, the spectrum is not, many things are not generic. For instance, it's not generic to have neutralinos as the lightest supersymmetric particle. Also, you have some tendency to have staus and other particles that could be charged and would be a disaster, right? If you have R parity and you have a charged particle as the lightest particle, you would have a kind of dark matter particle that is charged. So, and also, so some people try to scan a little bit different supersymmetric models and see how generic it is to get the WIMP miracle, right? So when we identify our neutralino as a dark matter particle, supersymmetric neutralino, will we have the right relic abundance? And this is what you see here. It's a very funny, very interesting plot. I don't know how generic is this scan in supersymmetric models, but what you have here is you take many supersymmetric models, more or less random, you compute the relic abundance, and you plot in this histogram the number of occurrences that your model had relic density, for instance, 100 times the relic abundance, or 100 times the total density, and actually you see that this is actually very likely. So if the neutralino, the combination of these particles is mostly abino, mostly a combination of the hypercharged boson, the partner of the hypercharged boson, you have a very strong tendency of overproducing dark matter because these particles, they interact very weakly. On the other hand, if your particle, if your main component of your neutralino is a wino, you have the tendency, because winos apparently they are more strongly interacting, you have the tendency to underproduce dark matter. And at least when you do this kind of scans, so it's the WIMP miracle in SUSY, it has to be taken plus or minus 2 orders of magnitude, which is not bad. It's not bad because if you ask the same question to the Axion, you will have a flat distribution here, but of many orders of magnitude, from the Planck scale to 10 to the 9 GeV or so. So 10 orders of magnitude against 6 or 5 is not bad. Very good. So as I was telling you, the neutralino and the neutrinos might be the favorite dark matter candidates, and the expectations are to have the right relic abundance for masses between 100, well, actually you can have these small mass solutions, but typically it's between 100 GeV and 1 TeV, you can have your neutralino dark matter. And yeah, unfortunately, the bad thing is that not all supersymmetric models and not all parameters have been tested, of course, because this is very large. So the people is trying to do constraint models and showing prospects for dark matter detection and so on with constraint models. But let me just move on. I'm giving you a little bit more exotic, another WIMP possibility, which is the possibility of having Kaluza-Klein resonances. So the idea here is very different, but it's also motivated to solve a hierarchy problem. So the idea is the following. The idea is that if we imagine that we have, we don't live in 4 dimensions, but more than 4, right? And so your gravitation, so the hierarchy problem, in a sense, is why the Planck mass is so different from the electroweak scale, right? So because all these particles that could exist, or maybe even Planck physics, could just take the Higgs mass to the Planck scale. So the Planck scale enters into the action of the standard model, just multiplying the rigidity scale, the gravity part of our action. Okay. But now imagine that instead of living in 4 dimensions, we live in 4 plus n dimensions. So instead of the Planck mass, we have to put here another scale. I decided to put something m squared, but I forgot this square. So but here appears. But now our axion has to be integrated over, of course, the whole 4 plus n dimensions, right? So if I do now I have to, of course, assume that my extra dimensions are compact to some extent because we don't see them. We don't have any evidence of being able to propagate in the 5th dimension, for instance. So I could just do an effective field theory by integrating the degrees of freedom of the 5th dimension. And this means I have to integrate over some volume my dimensions, okay? And when I do this integral, I essentially, what I get will be a 4-dimensional theory multiplied by some expression that depends on the fields, but the first order would be just a constant. And this constant is just the integral of the whole dimensions of the metric, and essentially, well, the R term, and it will be proportional, this constant, it will be proportional to this m star. That is the real Planck, will be the real scale at which gravity effects happen. And so then we come to this interpretation. If we call this a given volume, then we will turn out to our 4-dimensional theory, and we will be able to identify the Planck mass here with my fundamental scale of gravity multiplied by some volume. So the idea is very simple. If this volume of the extra dimensions is sufficiently large, and sufficiently large is sufficiently large in Planck units, we can have, in principle, the fundamental scale of gravity at the TeV or multi-TeV scale, and not at the Planck mass, just simply because we are being fooled by gravity looking 4-dimensional and the universe looking 4-dimensional, but in reality we live in, I don't know, 8 dimensions. And yeah, gravity becomes much stronger as we go to shorter distances and we start resolve these things. So of course, if m star is at the TeV, then there's no hierarchy problem. There's no surprise that the quantum gravity scale is at 10 TeV and the Higgs is at 1 TeV. A small hierarchy is okay. So, but this idea comes with a couple of nice implications, at least in some models. For instance, well, essentially, you can have, if these extra dimensions are compact, you can just, and for instance, they are periodic, you can always expand the wave functions of particles, or the wave function of particles in the extra dimension in harmonic powers, right? So you can have the 0 mode, the first mode, the second mode, etc. And now the idea is very simple, is that, for instance, imagine that you have only 1 dimension and you have this extra dimension. Now the idea is that if you have conservation of momentum in the extra dimension, right, which is, so you have, for instance, if this coordinate is periodic, you can have, you have Lorentz symmetry also in this 5th dimension, and then momentum has to be conserved also in the 5th dimension, okay? But this means that, oh, sorry, maybe I should have told you this. Sorry, sorry. Let's start by writing the dispersion relation of a particle in my 5 dimensions. Now is the mass, and then I have momentum in the first, and the second, the third, and also in the 4th dimension, right? Very good. Now the idea is that the momentum in the 5th dimension corresponds to precisely these oscillations in the wave function in the extra dimension. And since this only can have a finite number of values, this is quantized, okay? This is just 0, 1, 0, etc. So the idea is that the particles that we know might be the particles that have a flat distribution in the extra dimension. Okay, we are in the level 0, but we can have essentially particles that are the level 1, okay? And the particles with level 1, they get a mass, which is essentially what we would see in 4 dimensions. We see this momentum in the extra dimension as a new contribution to the mass. So if this dimension is inverse TeV or so, these particles will be all having TeV scale masses, okay? But what is more important is that since we have conservation of momentum in the 5th dimension, now the lightest of the Kaluza-Klein mode, so the lightest of the n equals 1 excited states, if you want, cannot decay to standard model because this decay would not conserve momentum in the fifth dimension, right? So here we have another example of how we can have kind of symmetry that prevents our, so we have, of course, many new particles at the TV scale, and the lightest of all of them is stable thanks to some symmetry. Before it was R parity, and now we have Lorentz symmetry in the fifth dimension. That's cool. Of course, one can, many people has worked in these models, and then one can just work out the spectrum depending on the geometry of the internal dimensions. And I just wanted to tell you, typically, yeah, exactly. So we can look for the first excitation of the standard model particles that has a free parameter, which is the typical size of the extra dimension that moves all the particles up and down. But each particle in the first level is not exact. Well, in principle, it has the same interactions than the particles at the zero level. So it's very easy to identify. It's very easy to do the phenomenology with Kaluza-Klein particles because they have the same interactions than our standard model particles. However, because they have different masses, they get also different radiative corrections, and they can get some hierarchies and some small differences in the spectrum that will produce some splittings with respect to the splittings of the standard model particles. And also something I wanted to tell you is that typically, or very typically, the Kaluza-Klein, the first excitation of the photon, the photino, not photino, I don't know how it's called. The Kaluza-Klein photon is typically the lightest particle in these models. So this will be the candidate. So let me just now go, so I've given you a couple of examples of WIMPs, but now let us see how can we actually find these WIMPs. The great idea of being motivated by particle physics theories is that all these particles, they have interactions with the standard model. This is a requirement of the WIMP miracle, right? Of these particles being produced in the early universe. They have to have interactions with the standard model. And now we can just look for the effects of these interactions in the three different ways I was telling you before. Direct detection would be just having a detector here and waiting until some of these WIMPs interact with some particle of our detector. Indirect detection, which means looking for the products of the residual annihilations of some of these particles in interesting parts of the sky. We can also try to look for these particles directly by just producing them. So let me just go first to direct detection. This, of course, has to be very brief. Direct detection, so as I was telling you, imagine that we're living in a halo of dark matter, as it seems, and dark matter is made of WIMPs. Then WIMPs that interact with standard model particles. So we put a bunch of standard model particles in a box, and then we wait until one of these WIMPs collides with one of the particles of our box. And the typical recoil energy that the WIMP will give to our standard model particles is given by this formula. It's proportional to the dark matter mass squared. So the more massive my WIMP is, the more energy is going to be in my detector. It's proportional to the velocity squared. So very low WIMPs are very wimpy. And it's inversely proportional to the mass of the nucleus that I'm considering. So more heavy nuclei, of course, they require a much larger momentum transfer to get a given recoil energy. So the different direct detection experiments that we have, that our colleagues have developed, they are based, or they're different in the way that they try to measure this recoil energy, okay? So the idea is that one can try to measure this recoil electron can produce some ionization in the medium, and you can just try to measure the electrons that have been just put out of their place, so the ionization charge. This nucleus moving in your detector can produce some light, some scintillation, okay? Or also can simply just scatter randomly of different nucleus and just simply hit a little bit your detector. So you can try to measure the effects of this recoil by just looking at photons, looking at charge, or looking at temperature of your detector. And yeah, there are a million experiments in the world looking for these things. So here you have the typical spectrum, the number of events per unit recoil energy as a function of the recoil energy. Typically, what you get is a signal that peaks at very low recoil energies, okay? Unfortunately, and that is also enhanced so you get a typical, well, at least, yeah, sorry. This is a bit tricky. So, of course, depending on the interactions of your WIMP with the nucleus, you can have different behaviors. So here I'm going to concentrate on the simplest WIMP that has what we call spin-independent interaction with nucleus. So it means that it's really, so it can have, so when a WIMP scatters with a nucleus, it can couple to the nucleus as a whole and not to the individual particles. So the cross-section will depend on the number of all the nucleons at the same time. So you typically have an enhancement of the rate, of course, that depends with the mass, with the atomic number of your nucleus. Here you have the typical cross-section. Remember that before I've given you the cross-section in centimeter cube divided by second. So if you divide this by the velocity of light, so the 10 to the minus 26 centimeter cube divided by second, it becomes of this order, 10 to the minus 38 centimeters squared. This is the velocity of a typical dark matter particle in the halo, and this is the typical estimate that we get for the density of these particles today. So we get, so on top of this spectrum, typically picked at low energies, where also the backgrounds peak, we get an extremely small number of events, like few recoils per kilogram per year. And these cross-sections have been excluded since some time. So this is a summary of how we express the results of these experiments. It will be very familiar to you. This is the WIMP nucleus cross-section, so the cross-section of our WIMP to give recoil energy to our particles in a box. And this is the WIMP as a function of the WIMP mass. And you have many of these experiments have been searching for these recoils and have not observed anything that looks like dark matter, or at least to a good significance. So they can just exclude values in the regions above these lines, okay? And I will tell you a little bit about these regions here, which are not exclusion regions. So the basic idea is that we have two main techniques, which are perhaps worth reviewing in this business of direct detection. Actually, we can, so in order to improve these limits, there are like two strategies, essentially. So in order to lower down so the concept is that, so what you can ask yourselves why this thing goes up here, and it's because of these experiments, they have to put a threshold. They have so much background at low frequencies that they have to put a threshold and not count anything that goes at very low frequencies. But what happens when the WIMP mass is very small is that you saw that the recoil energy is proportional to the WIMP mass squared. So small mass WIMPs, they give you very little recoil energy, and therefore you get inside of the threshold, okay? That's why these sensitivities, they go much high, very bad. And the only experiments that survive here are those that have a very, very light nuclei. Remember that the mass of the nucleus that is recoiling, it goes in the denominator of the recoil energy, so that you can have more recoil energy for a lighter nucleus. So the idea is in order to probe this region, if it's of interest, the idea is to lower the threshold, so somehow working with a lot of precision to your detector to lower the threshold and to lower also the atomic mass. And here, the only thing that matters is just more volume and, of course, lower background and measuring for a longer time. And the last feature that you see here is a region that is commonly known as the neutrino floor. So these are the values of WIMP scattering cross sections that are of the same, so that they are below the cross section for neutrinos to produce the similar, to produce nuclear recoils. So we have a WIMP here. A WIMP here will have 2 orders of magnitude smaller cross section than the typical background of neutrinos from the universe. This means that we will have to somehow, so for one event of WIMP, we will have 200 events of neutrinos. So it will be extremely difficult to disentangle between neutrino recoils and dark matter recoils. So here we will have a real hard time to find WIMPs. Very good. So actually, these 2 regions, they correspond very nicely to 2 experimental techniques to search for dark matter. The first, at very high masses, the winners, so that the most important and most interesting detectors are noble liquid time projector chambers. So the chambers, and here the idea is that the WIMP recoils produce some ionization. The WIMP recoils, the nucleus produces some light, which is this called signal 1. But then it also produces some electrons, so it ionizes something in the medium, and these electrons are just accelerated by a voltage difference, are attracted towards here the cathode, and then when they cross here, they emit some light that can be also observed. So we have 2 pulses of light, one from the prompt recoil, and then from the ionization that it produced. So we can distinguish between a nuclear recoil or a gamma or beta, other different backgrounds that we could confuse in principle with a WIMP by just the ratio of the light to the ionization. It turns out that, if I remember correctly, so gammas and beta particles that could also mimic our energy deposit, our WIMP energy deposit, they produce a lot more ionization than scintillation light. So as long as this S1 is sufficiently large over S2, you can just say, oh, this guy is most likely a WIMP. On the other hand, so the very nice technique is that you can build huge volumes, you can put huge mass in these detectors, and you can put so much that you can actually use the external volume of it as a shield. Because here there are always surface, well, of course, you have radioactivity from the halls of your lab. These detectors, as you know very well, are put underground, so they are isolated very nicely from cosmic rays, but they are subject to radioactivity of the rocks and of the materials, that residual radioactivity of the materials. So one normally uses a small volume around one defines a signal region and a small volume around this signal region where events will be taken as background, will be taken as coming from radiation that comes from the outside and not from a WIMP that has the same probability of interacting in the whole volume. So the second technique are millikelvin bolometers. So here the idea is you have to put really very small mass of a crystal. Here small mass is very critical because what you are going to measure is the temperature increase when your WIMP recoils and transfers some energy to the crystal, okay? And the idea is that, this crystal is thermally connected to a transition edge sensor. Essentially, well, that when you change the temperature, it changes the conductivity, and then so you can get a big signal out of a very small temperature increase. But of course, in order to get a temperature increase, which is measurable, I mean, these objects have to be relatively small. Otherwise, you have to share all the energy with a much larger crystal. So here, in this technique, you would go to larger masses to have more sensitivity by building many small crystals and measure each of them separately. And here you have some of the 3 competitors, Super-CDMS, CREST, and Edelweiss, using germanium or silicon detectors. And CREST uses this calcium tungstenate or something like this. So it has the advantage that this crystal has oxygen calcium, and tungsten. So you have 3 different possible nuclei to recoil. And oxygen is relatively light. So with oxygen, you can search for relatively low mass WIMPs. And actually, this is what these techniques are better at. So they can have light nuclei, so have larger recoils, but also they have excellent energy sensitivity because of they have much lower thresholds typically because they can measure really very small temperature signals. So these experiments are actually the ones that are going to beat at the lower end. These are the last results of the latest results of CREST of a couple of years ago. And you can see how they are able, actually, thanks to oxygen, to go really low in dark matter particle mass, although the cross-section is perhaps, but still compatible with being a WIMP to some extent. And these are the xenon results based on liquid xenon of essentially 4 weeks ago, or something like this, in which they improved over the competitors, LAX and Panda X, by a small amount, as you can see. So these are the bounds, the black line, in always the same plot, always for spin dependent. So let me just say a few words about indirect detection. So for me, the most important is direct detection. That's why I wanted to talk about it first. So yeah, I cannot have enough words of support for the people that are doing these direct experiments, because they might give a very strong signal that one can really understand, even if now we know that will become at a huge effort, because now the rates of events that we are expecting in this next generation of experiments is really, I mean, events per ton per year. So we are talking about very few events. But we can search for signals of dark matter in different environments and search, and find some inspiration for our model building and for direct detection as well. And we can also have some complementarity if we look for dark matter signals somewhere else in the universe, even if now the signals are not embedded in a laboratory that we can control. And actually, they are embedded in a laboratory which is extremely complicated, which is the small-scale structure of the universe. So the idea here is that even if the dark matter abundance has freezed out at very high redshifts when the temperature of the universe was huge, of course, this only means that on average, one WIMP will never find another WIMP to annihilate with it, on average. But this doesn't mean that some of them, they don't find their partner. It's only that the amount of these guys that will find their partner is not significant. Not significant for the relic abundance, but it can be quite significant for us seeing something, okay? So that's the idea. And actually, the relic abundance calculation was done for a homogeneous universe, right? That is decreasing its energy density. But actually, nowadays, the universe is not dense, and we know that dark matter is more or less clumped in halos around the galaxies. So actually, in dark matter halos, we have an overdensity compared with the average density. And also, even if not a lot of WIMPs are going to decay, we can still hope to find some of the things that they produce when they annihilate, because they have to annihilate into standard model garbage. So in this garbage, we can have essentially all the standard model particles, in principle. So depending on the model, we will have quarks that will hadronize into hadronic cascades. We can have leptons, we can have bosons, and quarks and bosons, they will hadronize, or very likely they will hadronize, they will produce pions, they will produce gamma rays. So we will have essentially every particle that we can find in the standard model can be a product of these annihilations. So we can, at the end, we can look for different signals of dark matter annihilation around us in the galaxy. For instance, 2 dark matter particles annihilate and produce gamma rays, photons. They can even produce a monochromatic line if they annihilate into 2 gamma rays. But they can also produce protons or antiprotons, very massive particles that actually they more or less they travel through the magnetic fields of the galaxy, and they can reach us, or if they annihilate close to us, they can also annihilate into electrons or positrons that they don't travel very much in the galactic magnetic fields before they lose their energy. So we can find high energy electrons, high energy protons or antiprotons, photons, and neutrinos that are missing in this plot. And actually, we can look in our galaxy, but we can also look at many different places in the sky. So here, this is a summary that appeared in a review paper in Nature a few months ago. By Jan Conrad and by Jan Conrad. So the most interesting places to search for dark matter annihilation would be where there is more dark matter, right? And we know from dark matter simulations, in principle, that the best place to look is the galactic center. This is where the dark matter is larger. It doesn't mean that it's dominant or is much larger than the baryonic matter, but it's definitely more abundant in the galactic center than at the position of the sun. At least simulations say so. So we could just look for something coming out of the galactic center or an extended version around the halo, around the galactic center, what is called here the galactic center, or the halo around the galactic center. And then we can also look outside of our galaxy in places like dwarf spheroidal, so small galaxies that contain more matter than visible matter, and therefore they have very low backgrounds. And these are going to be the two extreme strategies for searching for indirect searches. We can look for a place in which the signal can be very large, but actually we'll have a lot of uncertainties because the galactic center is filled with cosmic rays and sources, and it's a very violent environment. So it's going to be very difficult to model the expectations, the background expectations. On the other hand, dwarf galaxies, they have really, they are far away, so we are going to receive a less signal for sure, but at the same time, they have large, so they are super quiet places, really quiet places. So if we see something, this detection will have much higher significance because the backgrounds are much smaller. Nevertheless, so the signal is so small that with one dwarf galaxy, we don't do much. However, here the winner can be, and it is in some cases, just combining the results of many small galaxies, so the expectations from many small galaxies. And then we might have a strong signal if we combine the expectations, but more or less understood systematics. So yes, this was how to highlight the typical experiments that are looking for this for our messengers, the messengers that are carrying the information from dark matter annihilation. We can, of course, measure gamma rays with the Fermi telescope. This is a dedicated satellite hosting a calorimeter to search for gamma rays, producing electron-positron pairs here. But we can also look for gamma rays of much higher energies. So if our dark matter mass is much larger, you can produce gammas which are much more energetic, and these gammas when they enter the atmosphere, they produce electromagnetic showers that we can detect with these Cherenkov telescopes like MAGIC, HESS, and the Fusion CTA. And when we produce antimatter, which is or cosmic rays in general, we can use another satellite, the AMS satellite, to measure the antimatter. Or if we have neutrinos produced from dark matter, we can use IceCube or Antares. Okay, but I think I will not have time to talk about all of them. Let me just talk about gamma rays because I think they are more or less a relatively clean source, and there's actually something to be said. So the idea here is that our WIMP can just annihilate into something and produce some gamma rays. We can just, for instance, let me just first focus on the galactic center. We can just model the emission if we have a particle physics model and a dark matter model, and we can just, and we have, for instance, the observations from the Fermi satellite as a function of frequency, just number of counts. This is a map of the gamma ray sky done by Fermi. So we have to model our signal and compare with observations, and then we find that essentially the signal is typically hidden behind a lot of background, so we have to model the background. So we have to try to understand why all these gamma rays are coming to us, and we can actually more or less do so because because Fermi has information at many different energies, and we have information about the galaxy from many different channels. We have radio emission, we have gas maps, we have plenty of information that we have to combine in order to build more or less a map for the emission of gamma rays of the galaxy, and then see if there is some excess, if this map shows some excess like this when we account for all the emission. And let me just go over this essentially. So there were for some years there were just strong constraints, but a couple of years ago, a couple of groups reported that when they did this exercise, they just searched for gamma rays, they modeled the background, subtracted signal minus background, and they still observed a residual emission from the galactic center. And here's the spectrum. And actually, they could fit the spectrum of gamma rays coming from here, from the galactic center, very nicely with the dark matter hypothesis. With a dark matter particle annihilating, for instance, to a BB bar or tau plus, tau minus. Let me just go to the most recent results. This excess is actually persisting. So here are the results of the Fermi collaboration. The Fermi collaboration is the collaboration ruling the Fermi satellite and Fermi experiment. And they, of course, they have done they are known for being a very conservative collaboration, and they don't like very much to claim any dark matter discovery. So after the analysis of some independent groups, of course, they have done their own analysis. And this is what you see here. So what you see here is what they have done is that they have tried all the background models that they could think of, changing all the uncertainties that they could think of. So much more than previous analysis. And they are showing here the flux of gamma rays from the galactic center as a function of energy. And this region essentially covers all the models that they have found by varying the uncertainties. So this is the residual. So this is the residual over the background. So actually, they still see a signal. So they see an excess. The only thing is that clearly they cannot quantify this excess, right? So because you see, it has very large error bars, particularly at low and high frequencies. So what they say is that essentially that this uncertainty can be of order factor 3 up and down, and what is also very interesting, they point out that actually they find when they look, so they do cross checks like this. So they look at the galactic center, they find this excess, very nice. But now they look in the galactic plane at other region, and they see whether there they find an excess or not. And actually, they see in many places along the galactic plane, they see excesses which are similar to this. Of course, the signal is much smaller because in the galactic center you have more stuff, but the ratio between the excess and the background, so the signal in background, is very similar in these excesses. So they warn the readers, us, to say, okay, maybe it's even a larger uncertainty that we have not taken into account, or they have different explanations for this, possible explanations. For instance, a leak from a gamma ray feature, which is called the Fermi bubbles. They can be also cosmic ray interactions from result sources, so cosmic rays sources in the galactic center, but also these gamma rays can be generated by unresolved sources, by some sources that are in the galactic center, but we cannot see, like these millisecond pulsars that were mentioned already some time ago. Nevertheless, so they say, even if we still see some residual, we cannot claim a discovery, so we are going to put just constraints. The constraints are not going to be very large, because the constraints will be they can put a constraint on the flux of gamma rays coming from dark matter, right? That's a concept. But of course, since these can be signal, right, the constraints are going to put, they correspond to fluxes above the galactic center excess. Nevertheless, so you have here the plots, and for these analyses are all model dependent and assumption dependent, but you can get a sense of the comparison by just looking here at the cross-section, annihilation cross-section of a WIMP, okay, as a function of the WIMP mass. And what you have here is, first of all, the assumption that the most important channel of annihilation is BB bar, which is a typical annihilation channel of a WIMP with these masses, okay? BB bar then hadronizes into bottom quarks. They typically hadronize, and the hadronization cascade, you produce pions, and these pions decay into gamma rays. And these are the gamma rays that we will be seeing, okay? So these two lines, the black and the red, they correspond to the constraints that the Fermi can put. And they differ only in the dark matter profile close to the galactic center. Okay, the dark matter density close to the center is actually very important and is not well constrained at all. It's very important because the flux of gamma rays coming from the galactic center or from any place in the world is proportional to the density of these particles squared, right? Because the number of particles, so you have to have one particle and other to produce an annihilation. So any uncertainty in the galactic center is amplified by this factor squared. And yeah, so you see that there is a factor of a few difference even in these two models, which are NFW, which is a standard halo model that is actually very well supported by some simulations. But changing a little bit the parameters of the NFW model, they can get a factor of order 1, as you see, a factor of order almost 2 in difference of the constraints. And these regions here were the regions that 3 different collaborations claimed that they could explain. So the WIMP in this region could explain the excess, okay, or here, depending on the estimate. As you see, more or less, one cannot conclude very much from this channel, but and even less from the assumption that our WIMP somehow doesn't like quarks and likes to annihilate into leptons, like for instance tau anti-tau. Essentially, yeah, so some groups would put the explanation here. Some relatively more strongly interacting WIMPs will be excluded. And yeah, and here maybe what I wanted to call your attention is the fact that in principle, some of these regions would be compatible with the thermal relic cross-section that I showed you before. So this would be a WIMP, the miraculous WIMP, right here. So it's actually very interesting to search for these particles, but maybe not so here. This region really is particularly excluded. So maybe this example is more interesting. But here you see another line. And this corresponds to an exclusion line that has to do with the other possibility that I mentioned before. So instead of looking at the galactic center and model all these backgrounds, why don't we just look at the simplest places where we can find dark matter in the universe? Why don't we look at these dwarf spheroidal, these dwarf galaxies? And this is what the Fermi telescope can also do. So in the last paper, I think it's from a couple of years, this is the last that I could find at least, is doing exactly the same exercise. It's just looking at actually 15 dwarf spheroidals, is measuring is estimating the amount of dark matter in these objects and estimating the probability, the annihilation cross-section, etc. So the signal in gamma rays from these objects. And it's combining all this signal and combining all the background models. There are not many backgrounds. And by comparing signal to background, they can put, so actually they don't see any signal above the background, so they conclude only we can put upper limits, And these upper limits are these black lines here, depending on the annihilation channel, BB bar or T plus, T minus. And this is the line that you see here. That is actually excluding this interpretation, but not a very strong significance. So there might be still room for a WIMP to explain this GeV excess. And this is, of course, only one model. So one can just play with different models, and perhaps these things, this excess can still be due to WIMP dark matter. So let me tell you about something also very interesting. This was just diffuse gamma ray emission. So just our WIMP annihilating into BB bar, and then this BB bar produces some pions, and then you get more or less a spectrum, right? That the spectrum that you saw of gamma rays. But actually, there's a very nice channel to identify dark matter, which is a channel in which the dark matter annihilates into monochromatic particles, like, for instance, photons. Okay, can annihilate into 2 photons. And that each of these 2 photons will take the energy of one of the 2 WIMPs. Okay, so we will have a signal, a monochromatic signal of photons. This monochromatic signal is, of course, not seen as one frequency, because our detectors, they don't have very good energy resolution. But this is a very clear signature of WIMP dark matter, because we don't know any other particle that is at rest in the galactic frame and can just decay or can produce monochromatic gamma rays. So we don't know any. So if we would have a source of non-relativistic Higgs bosons, right, we would see gamma rays at 60, with a very small probability. We would see a peak at 60 GeV, right, 60-something GeV, half of the Higgs mass. But we don't have any non-relativistic source of Higgses, for instance, or nor of any of these particles. All the backgrounds, all these high-energy particles produced in the galaxy, they come from cosmic rays as accelerating charged particles, and these always have smooth distributions. So here the idea is very nice then. So I don't have to know very well my backgrounds. I can just assume that they're always smooth. So I can just feed them locally with a power law and just search for a line on top of this power law. The bad thing to pay is that typically this annihilation cross-section is suppressed by a factor, by a relative correction with respect to other annihilation cross-sections. So you have a price to pay, which is a factor of 10 to the minus 3 in the cross-section, okay, typically. So that's why here you see numbers which are of the order of 10 to the minus 30 and not 10 to the minus 26 centimeter cube second that we saw before. So okay, this is an analysis that the Fermi collaboration can also do, and they just, you see, fitting the background by a power law plus a little bump at some place. And then if they can see how big this bump can be, and they put constraints on the size of these bumps, and you get these funny constraints that are so wiggly, because of course you can always have local excesses.
Since we only have 1 photon from the annihilation, does the boost of the system matter? Boost of the system affect the
So here the assumption is that these particles are produced essentially at rest, right? They have velocities which are 10 to the minus 3 of the speed of light. So I think that the boost is 1, right? Yes, I guess you meant that. So there was a lot of excitement actually some years ago, a few years ago, because actually a couple of groups, they were studying the gamma ray data, and they found actually that doing very clever cuts in the data and modeling the backgrounds with power laws, as always, actually they found choosing also, one had to use some techniques which were a little bit Machiavellic, but choosing the right places in the galaxy, they could just really find an excess that showed a moderate level of significance. At some point, we were talking about 4 sigma excess over the fitting background, but unfortunately, it didn't survive. Statistics, so more statistics came, and the significance went down. And also, a much better model of, and I think this was the key, if you ask me, a different model for energy calibration, so the energy reconstruction. So what Fermi measures is a series of parameters from their box, right? So this box outputs some parameters, and from these parameters they have to reconstruct, they have to give the energy of the gamma ray that produced these parameters, this collection of electrons, et cetera, et cetera. So they have to reconstruct the energy from the raw data. And they have been doing improvements in this reconstruction throughout the years. And of course, they're getting better and better. But these algorithms to reconstruct the energy, they might not always be very smooth. Okay, these algorithms can also show some features, because you can put thresholds, cuts, and I suspect that some of these photons were coming from some possible effect in the energy reconstruction. Because actually, when you look at places where you don't expect dark matter annihilation to come from, they were also seeing small excesses, like in the albedo and so on. Well, since I don't have a lot of time, I'm not going to tell you about other type of dark matter that can give you photon lines, but you can ask me later about stellar neutrinos. You can ask me. Not talking about antimatter, perhaps. And I just want to finish by just saying that, of course, we can search for the dark matter particle without the assumption that that is this forming the dark matter. So we can just try to produce it in colliders. This is what we are doing with supersymmetry, right? We are trying to identify supersymmetric particles in collider experiments in the LHC. But here, so if supersymmetry exists, and also the lightest supersymmetric particle is the dark matter candidate, or a neutralino is the dark matter particle candidate, the two things, they marry really very well for LHC searches. So the idea is that you can have signatures of the existence of SUSY that very strongly rely on neutralinos being dark matter or being very long-lived. And this gives you this type of phenomenology, which I think marries very well. So you have a one proton, so you have collisions of 7 TeV protons in the LHC now, and you can just produce jets and blah, 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 blah. And in the final products of your collision, you can produce a neutralino, a WIMP. And this WIMP is a stable particle, so it disappears from the detector. It's also neutrally charged, so it has no electric charge, so it doesn't interact with the detector around the collision point. So it simply appears as missing energy, missing momentum. So when our colleagues in colliders, they try to reconstruct what happened in this collision, they often find, or they expect to find events in which they sum all the pieces and they are missing some. And that this missing piece can be actually due to the dark matter. And actually, many of the searches for supersymmetry in the LHC are based on this, are based on the prejudice that the dark matter will be supersymmetric, and we will have a signature of this type. This is extremely useful because these techniques have been developed very nicely, but it's also very dangerous because it might be the supersymmetry is there to solve the hierarchy problem, but some of the dark matter candidate, like a stellar neutrino or a Kaluza-Klein or whatever, or an axion, why not, is the dark matter. So it gives most of the dark matter, right? So our parity, this parity that we have to invent, impose, or use in supersymmetry to have a stable supersymmetric partner as dark matter doesn't have to be conserved in nature. It was only something that we have invented to have dark matter. So it's only a small subset of supersymmetric theories have our parity, conserve our parity. Okay. But besides the searches for supersymmetry, we can, and just the last thing that I wanted to tell you about, we can also do, and this is something very interesting in colliders, we can do model-independent searches. So we can try to search for really the production mechanism I was advocating before. So if in the early universe, dark matter particles could annihilate into standard model particles, in our colliders, we can have the same. So we can just have really annihilation of quarks and gluons of our protons and into our dark matter particles. Okay, WIMP, anti-WIMP, or WIMP-WIMP. And then the idea is, and this has been done these processes have been studied by CMS and Atlas. Of course, so the signature is, as I was telling you before, essentially, in principle, the zero signal would be just you have two protons colliding and nothing happens. But this is very difficult to distinguish because they typically have, I don't know, something like 10 to the 7 protons going in one crossing, so they cannot count them all. So if some of them disappear, something like this, or and actually it's not the proton that would disappear, it's just some quark, and then the proton would hadronize and most likely will be lost. So the idea here is to look only for collisions that have a large transfer of momentum to the dark matter, okay? Because in that case, and also collisions in which we can have emission of some standard model particle to make sure that this transfer was very high, okay? So high momentum transfer and some particle to tag that takes also part of this momentum transfer, right? So then in these cases, we can just search for dark matter in a more or less model independent way, just from the diagram I showed you before, okay? So this, just searching for this monophoton or a monojet, so gluon that hadronizes, or mono W decaying into lepton and neutrino, or into a C that decays into leptons or to jets. And you can get this, so of course, I wanted to show you, of course, there are some standard model backgrounds to this, right? Because we can have, imagine, you can just produce a jet from the anti-quark annihilation and then radiate a W that decays into two neutrinos. This would look, if the jet is emitted with a large transfer momentum and this neutrino pair is emitted with a lot of transverse momentum as well, so you have this collision and they go like this, you would see a jet down and nothing going up. And you can say, oh, this looks like dark matter. But no, you have to study these things. You have to calculate how often they happen, and you have to subtract and take this background into account. And when you do this, you get results which are perhaps not so encouraging for spin-dependent annihilation cross-sections. Here what you see is really the WIMP nucleon annihilation cross-sections. It's the same that we were seeing for direct detection. Sorry, this is translated to the scattering cross-section, I guess. As a function of mass, here you have all the limits from direct detection, and you see that collider searches are relatively good. So they extend to very high masses and so on, but actually they are not so good. So they cannot probe very large cross-sections. And this is because of the backgrounds and luminosity. So with more luminosity and better control of backgrounds, in principle, we could go down. But you see how many orders of magnitude they are compared with colliders. But the situation completely changes if you consider spin-dependent interactions, because in this case, the direct detection limits are just much worse, because the cross-section for spin-dependent scattering is suppressed, is velocity suppressed. So you get down a few orders of magnitude with the direct detection, and then is when the LHC can be extremely complementary, as you can see here. It's much better than dark matter experiments. So I think the complementarity is very nicely highlighted in this last slide, I promise, in which you see the cross-section, the annihilation cross-section of WIMPs into standard model particles in a generic case. I think this is, and you see here the future, the sensitivity of xenon 1 ton and the sensitivity of xenon n ton, so a much larger version of xenon that it will take place eventually. And what you see here is the parameter space that could be filled, that could be populated by different supersymmetric models that have neutralino as dark matter candidate. So the neutralino could be anywhere here, as I was telling you before. And so the complementarity is more or less understood in this way. So this blue region is relatively easier to find supersymmetry in the LHC. Sorry, you have to look at the numbers here, and you have to be surprised by this centimeter -2 here, right? I think that's a typo. Okay, so nevertheless, so yeah, supposed to at low energies, we have seen that actually indirect searches can give us some information at this small range, but here it would be the LHC for spin dependent that could actually make some discovery. There will be a transition region in the future where collider experiments can be complementary to gamma ray searches, and at very high frequency, it will be gamma ray searches what could say something about dark matter. I didn't tell you about the future of gamma ray searches, but I showed you here this complementarity between GeV experiments at low frequencies and Cherenkov telescopes at very large frequencies. And it turns out that the community is preparing a next generation, a large-scale Cherenkov detector. It's called the Cherenkov telescope array that will be many orders of magnitude more sensitive, or some orders of magnitude more sensitive than current Cherenkov telescopes. And thus, we will improve very strongly at very high energies the gamma ray constraints. And with this, I hope I gave you some overview of the different very interesting signatures that WIMP dark matter can have in the universe and in the lab. Thank you very much.